So, in the previous classes, we introduced Faraday's law, right? And we applied it for many examples. And first we introduced Faraday's law in this form, right? You remember we had EMF equals to minus a rate of change of the magnetic flux. Basically, what does it mean? So if you have, for example, any conducting loop, right? And if it is exposed to the magnetic field, as a result, you have magnetic field, you have a loop. As a result, there is a magnetic flux. And if that magnetic flux changes in time, then somehow electric EMF will be produced in this loop. And as a result, induced current will start flowing clockwise or counterclockwise. It depends on the situation, right? So we discussed how to find the value of EMF, how to find the direction of the induced current, right? And then, okay, it's universal law, right? But at a certain point, I told you, right, everything is great about this law, except from a point of view of fundamental physics. EMF is not the quantity which we want to see. EMF is great quantity mainly for engineers, right, experimentalists, technicians, right? Again, from the point of view of fundamental physics, it's better to have there, instead of EMF, electric field. Magnetic field is there, right? It is inside of the flux, but it's better to have electric field in order to have the most general form of the Faraday's law. And we've made that replacement in our previous lecture. So as a result, we rewrote this Faraday's law in the most general form. And we introduced it in this way. Integral over a closed loop E dot ds. It's an infinitesimally small element of that closed loop, and it is equal to minus d phi over dt, minus d phi magnetic flux over dt. So that is the most general form of the Faraday's law. So if you open any book to see Maxwell's equations, you will see this form of the Faraday's law in the set of Maxwell's equations. So what's the structure of this law? Basically, it tells us that changing in time magnetic flux produces the induced magnetic field. Or if we dive even deeper, basically, what does it say? Changing in time magnetic field produces induced electric field, right? So this is a tremendous conclusion. It's something huge, right? You remember we discussed that. So let me tell that. So changing B in time, changing in time B produces induced electric field. So now you see electric field can be produced by magnetic field. It's something which is very, very important, right? Okay, so and now let's apply it for a solenoid, because most of the time we use a solenoid, right, to produce some uniform magnetic field. So let's apply this formula for a solenoid, right? We've done in our lecture, right? Right, so I will write apply it for a solenoid. Right. So what is solenoid? Let me sketch it. So let's say we have a solenoid, right? So current in, current out, right? Let's say and let's say current, for example, decreases, right? So here current is getting out. And of course, this current produces a magnetic field, right? Something like this I can draw. So that's our B. Since current is going down, magnetic field is going down, right? So magnetic field inside of the solenoid changes. dB over dt is not 0, and as a result, inside of the solenoid, we're going to produce, or magnetic field is going to produce the induced magnetic field. Okay, now let me draw a top view. If you, for example, look at this solenoid from the top, what are you going to see? So now let me draw a top view. All right. Okay, I think I should be able to fit it here. Right. Okay, slightly compressed. So let's say this is our solenoid, right? Solenoid. This is the edge of the solenoid. And this is the center, right? Let's say the radius of the solenoid is R0, right? And since it's a top view, so what are we going to see? We're going to see a magnetic field will be represented by the dots or crosses. Crosses means out of us, right? Right. So magnetic field will be represented by these crosses, right? So that's B, this magnetic field which is going down, right? So what? Changing in time magnetic field is going to produce induced electric field, and we discussed in our lecture. So in this case, in the case of uniform magnetic field, electric field lines are circles. Magnetic field lines are circles, right? So let me draw something like this. Maybe I can draw more, right? So these are electric field lines, induced lines, electric field lines, right? So then, how can we find direction of these induced electric field lines? I said, okay, we discussed it in the lecture. What we do, all right, you just imagine a conducting loop. Of course, in our problem, there is no conducting loop, but every time when you need to find direction of the induced electric field lines, you just imagine a conducting loop, right? And then apply Lenz's rule, like we've done it so many times already, right? So see what happens with the flux, right? So then if flux is growing, that induced magnetic field will be in the opposite direction, then right-hand rule. So all those steps, right, which you should be familiar with right now, right? So let me right now. So direction of E induced or E induced direction. So how can we find direction of E induced, right? Direction of those electric field lines, right? So imagine which we wrote a metal loop, and then apply Lenz's rule, right? So apply Lenz's rule and you will be able to find direction of the electric field lines. In this case, what if we apply this? Imagine, for example, this is our conducting loop, right? And so what happens with the external magnetic field? Magnetic field is going down, right? Magnetic field is going down. So it means that the loop is going to be supportive, right? It's going to support dying magnetic flux. As a result, induced magnetic field will be in the same direction as the external magnetic field. So it means that within the loop we're going to have crosses representing induced magnetic field, and then apply right-hand rule. So in order to get crosses, I have to curl my fingers like curl my fingers like this, right? Curl my fingers like this, and as a result, induced current will flow in clockwise direction, right? And as a result, direction of the induced magnetic field will be also in the clockwise direction. So direction of these electric field lines are going to be this way, right? Okay, so that's how you can get direction of the induced electric field lines. Now magnitude, you can look at my presentation, right? How to find magnitude of E induced. E induced magnitude. Again, I didn't derive it in the class. We just discussed it, because derivation is application of, okay, we apply just Faraday's law for that case, right? It's a very, very similar to the application of Ampere's law. We've done it so many times, so if you just look it by yourself, you can do it, right, easily, right, at this point, right? And we just discussed it in the lecture. So we discussed and we found that if we are inside of the solenoid, radius of the solenoid is R0. So if we are inside, then expression for the induced electric field, right? So this induced electric field, right, equals to E induced equals to R over 2. R, it's a distance from the center to the point where you want to find the value of the electric field, and then times rate of change of the magnetic field, dB over dt. So it's this external. So this magnetic field changes in time. So you just need to know it rate of change multiplied by the radius and divided by 2. So you can see what will be the value, for example, of the induced electric field at the center of the solenoid. 0, because R will be equal 0, right? And electric field is 0. And then with distance, with R, electric field getting stronger and stronger and stronger, and it will be the maximum. It will have the maximum value near the edge of the solenoid. And what about outside? If R is larger or equal to R0 outside, the value of the induced electric field, the expression will be R0 squared over 2R, and again the rate of change of the magnetic field. So outside, magnetic field is going down as 1 over R. So we can actually plot it, for example, right, to have a better picture. So E induced versus R. So let's say this is the radius of the solenoid, R0. Let's say this is the line, and then inside, induced electric field is growing with R linearly, right? And then outside it decays as 1 over R, right? So here it's proportional to R, and here it's proportional to 1 over R, right? Okay, it's slightly not straight, but it should be a straight line. Okay, so that's the review of what we need in order to solve the next problem, and that problem is also in your homework, right? So problem 3019. So now let's apply these results to solve problem 3019. Right. So what do we have in this problem? We have a solenoid, right, which gives us a uniform magnetic field, right? Then we're going to take a proton, and of course we know we have information about the solenoid, right? The radius is given, how fast the magnetic field changes, and actually the magnetic field will go down, right? And then we will take a proton, stationary proton, and we're going to position it at several points near the edge, in the middle between the center and the edge, right at the center of the solenoid, and we will have to calculate the acceleration of that proton. But again, you need to remember that we're going to position it at a certain point and release it, so the initial velocity is 0. It's very important, right? All right, so we need to find acceleration at the initial moment of time. What's acceleration of the proton at certain points at the initial moment of time, right? Okay, so problem 19, and this problem is in your homework. So let me now outline, describe what is given. As I said, we have a solenoid. So radius of that solenoid is 2 centimeters. Let me convert immediately to meters. Okay. I don't like this overlapping. r equals 2 times 10 to the power of minus 2 meters. All right, then magnetic, so current of course changes, right, through the solenoid. Current is going down. As a result, magnetic field inside of the solenoid is also going down, and the rate is given. So dB, okay, you know, maybe I will close it, and then dB over dt, the rate of change of the magnetic field, absolute value is 0.1 Tesla per seconds. 0.1 Tesla upstairs, downstairs per seconds, and it is actually decreasing. So that is decrease. Okay, decrease. Save some space. Right, then, so we'll take a proton. So we have a proton, right? And initial velocity of the proton is 0. Okay, I will emphasize. It's an important parameter. You will see when. You will see at a certain point why it is important. And what we need to find, acceleration of that proton at a certain point. So we need to find acceleration of the proton. And then I will add at which point. So now I need to draw the picture, and then on the picture I can show which points we're going to discuss. So I need to draw a big picture similar to this, right? All right. I'm trying to estimate the amount of space I will need. Right, so that's my, this is the edge of the solenoid, right? So then radius of the solenoid is given. Let me draw it, for example, here. So that's R, right? This is inside and that is outside of the solenoid, right? And radius is given. Magnetic field, according to the statement of the problem, magnetic field is crosses, it means into the board. Right, so that's the magnetic field, which is decreasing. Okay, so now physics. About the points, right? So we're going to position this proton at a certain points. Which points I'm talking about? So I'm going to position it at this point. It's point A. It's a midpoint between the edge and the center of the solenoid. So that's point A. Then we're going to discuss point B at the center. Then point C here, the midpoint between the center and the origin. So this will be C. And then point D at the edge of the solenoid. So we're going to position the proton here. We need to find acceleration here. Acceleration, absolute value and the direction. And then here and then there. So we need to find acceleration. Right, so I will write acceleration of the proton at points A, B, C, D. Right, so these 4 points, right? So let me separate the statement of the problem, and now let's start discussing. And let's first discuss the physics, right? And then I will sort of outline the solution, and then we'll get into the details. So physics. No, probably I will mix the description of the solution with the physics, right? So first step, which we need to understand, of course, and realize. So we have magnetic field, which changes in time. It means that electric field is or will be induced inside of this solenoid, right? And electric field lines are circles, right? Circles. And we also know that we're going to position our proton inside of the solenoid, so we can use the proper formula to find the electric field, right? And then direction. In order to find direction of the electric field lines, we will apply Lenz's rule. right? So, and then a proton is going to interact with that magnetic field. It will experience the force and acceleration and so on, and acceleration, and that's what we need to find. Okay, so now let's outline the solution. So at the very end, we will have to find acceleration, right? Then, in order to find acceleration, I just start from the very end. So in order to find acceleration, we will have to apply Newton's second law, right? In order to make a transition from what? From forces or force acting on the proton, and then we will be able to find acceleration. Now, which forces should we consider? Of course, so far in this course of electromagnetism, we have two forces, two types of forces: electric force and magnetic force now, right? So let me write them down, right? So first one, electric force, F electric equals Q times electric field, right? And the second Lorentz force, F magnetic equals Q V cross B, right? So these two forces. Now, the author of the book who created this problem was nice enough. He said, let's assume that the proton is released. So initial velocity of the proton is 0, and we need to find acceleration at the moment of release at t equals 0, right? So if initial velocity is 0, so it means that what will be the value of the magnetic force at that initial moment of time at t equals 0? 0. Since V naught will be 0, so magnetic force will be 0. So basically the author gave us this condition in order to simplify our life. Otherwise, solution would be significantly more complicated, right? But since he said, let's assume that the proton is released, as a result, magnetic force can be dumped, right? So let me do this. So this is 0 since V naught equals 0, right? But again, it's only true at the initial moment of time. The next moment of time, right, the proton most likely will start moving, and then of course it will start experiencing magnetic force. But since the problem is about acceleration at the moment of release, so magnetic force can be forgotten. So we only have to discuss electric force. Okay, and plus, since we are dealing with the proton, positively charged object, so it means direction of a electric field and direction of the electric force are the same, right? So we don't have to adjust directions. Now, in order to get so force will be used to get acceleration, and then of course this we need to know this induced electric field, right, in order to find electric force. So E induced, right? So E induced. So what? In order to find direction of the induced electric field, we will have to apply this Lenz's rule. In order to find absolute value of the induced electric field, we will have to use one of these formulas, right? So, and of course, induced electric field will be there because there is a rate of change of the magnetic field. So magnetic field changes. As a result, electric field is induced. As a result, charge position inside of this electric field will experience electric force. And then since charge has a mass, it will experience some acceleration. So that's the outline of the solution. And now let's get into the details. And we will start with the direction. Basically, we will start from this point, right? So let's start with, I think I started with direction first. Yeah, let's first, E induced direction. E induced direction. So what do we have to do? First, imagine a conducting loop, right? And apply Lenz's rule, right? Let me write. So imagine a metal loop, right? I will probably imagine it over here, right? I will probably imagine it over here with dash lines, right? With the dash line. So this will be my imaginary conducting loop. Let me show that this is my imaginary conducting loop, right? And so what happens? A typical lens rule application. So what happens with magnetic field? Magnetic field decreases. The area of the loop stays the same. Angle stays the same. So basically I can write, so B is going down, right? B decreases. As a result, magnetic flux decreases. As a result, this conducting loop is going to produce induced electric field, right, in the same direction as B external. It means that, let me use some green color, right? So for example, over here, I will put a small cross. B induced will be in the same direction as B external. So, and then as the last step, right hand rule. So now I have to curl my fingers, cross it is into the board, cross into the board. So I have to curl my fingers like this in order to get the correct direction of the induced current. So current will flow in a clockwise direction. So as a result, I induced will be in a clockwise direction. And induced electric field all the time in the same direction as the induced electric field, right? So now as a result, E induced in a clockwise direction. So, so let me underline it. And so now I can draw, and of course electric field lines are circles, right? So now on top of these dashed lines, I'm going to draw electric field line. So that's my electric field line. Okay, let me show that this is my electric field line. In direction is clockwise. So it means this way, this way, this way, that way. And at point A, direction of the electric field up. Now I will use red because now it's important, right? So this will be my E induced at point A. Then at point C it will be down. So this will be E induced, and at point D it will be also down, right? At point B it will be 0. Okay, so now we know a direction of the electric field at all these points, and now let's recall the magnitude. Let's write down the expression for the magnitude. So this was for the direction. Now let's write E induced magnitude. Since we are positioning our proton inside of the solenoid, right? So we have to use this formula. All right, this is outside, this is the expression for the induced electric field inside of the solenoid, right? So I can write, so E induced equals to R over 2 and the rate of change of the magnetic field, right? Again, these are just absolute value. We know the magnitude. Right. So what's next? So we are over here. We know everything about the induced electric field, direction, and magnitude. So now we need to move over here to this point. So electric force, Q times this. So now, as a result, next step, F electric equals QE induced. So we'll just multiply by Q. QR over 2 and the rate of change of the magnetic field, right? And the final step. So now from here to there, acceleration. So using Newton's second law, acceleration will be equal this force divided by the mass. So downstairs we will just add mass, right? QR divided by 2m, right? So and then as a result, acceleration equals F over m, right? F electric over m. So I will just rewrite this QR over 2m and the rate of change of the magnetic field. So that's the expression. right, for the acceleration. And now we just need to apply this. This is acceleration correct at any points inside of the solenoid. R is the variable. R can change from 0 all the way to R capital. R capital. Right. So now we just need to apply this formula for all 4 points, A, B, C, and D. So let's do it one by one. So which point I started? Point A. So let's do it with point A. Right. Point A. This. Right, so direction is up, right? So we know acceleration will point also up, right? Because charge is positive. If we had an electron, of course, acceleration would be in the opposite direction. At this point, force, direction of the electric field up, and then force would be down, right? But in our case, since we have a proton, so everything is fine. So, what is radius r? R at point A. Point A is midway between the edge of the solenoid at the center, so it's R over 2, R capital over 2. So R sub A, it's R capital over 2. As a result, the expression for the, maybe I will write underneath, acceleration at point A sub A. Looks silly, but that's what we ended up. Right, so Q, R sub A, it's R over 2. Q, R over 2 divided by 2m, right? And the rate of change of the magnetic field dB over dt, right? Okay, so now we can just multiply it, calculate it, right? So mass, you know what, maybe I will write these numbers, right? So, of course, charge of the proton, it's a charge of the electron, but with plus, okay, I will drop the units, right? Then, R over 2, it will be 1 times 10 to the power of minus 2, 1 times 10 to the power of minus 2. Then, divided by 2 mass of the proton, 2 times 1.67 times 10 to the power of minus 27 kilogram, and the rate of change of the magnetic field 0.1 Tesla per second, right? 0.1, okay, here I will write Tesla per seconds, right? Okay, so now if you multiply it through, you will end up with, right, I will write underneath 4.8 times 10 to the power of 4 units, just the regular units of acceleration, meters divided by square of seconds. Meters square seconds, and direction, let me write the direction, upward, right? So that's point A. Now let's discuss point B. Point, okay, it looks, point B. Point B, at the center of the solenoid, right? What is the radius at point B? These are 0. So electric field is 0, electric force is 0, acceleration is 0. So it's not going to experience any force and no acceleration, right? So R at B equals 0, right? And of course acceleration equals 0. Acceleration at point B equals to 0. Point C. Point C, radius will be R capital over 2. As a result, it will be acceleration at point C will be equal to acceleration at point A, but direction will be opposite. Direction will be down, right? So point C. So it will be acceleration at point C equals to acceleration at point A, but downward, right? So let me write which way I wrote. So 4.8 times 10 to the power of 4 meters per square seconds, but direction is down, right? And the last point D, when we position a proton at near the edge of the solenoid. So now D. Right, so what's the radius at point D? R at point D will be just 2 times radius at point A, right? So R capital here will be just R capital. And so as a result, acceleration at point D will be equal 2 times acceleration at point A. Let me remove this. So acceleration at point D equals 2 times acceleration at point A, right? And direction will be, again, downward. Down, right? So it will be 9.6 times 10 to the power of 4, right? Okay, so that's the problem, and this problem you also have in your homework, and I know some of you asked me about this problem, and I told you that we're going to discuss in our recitation class. So now we've done it. Okay, so that's what I was planning to discuss today, and so thank you, and I'll see you next time.